Welcome to the exercises for chapter 19. Let's begin with exercise 1. The goal of exercise 1 is to demonstrate using SymPy and SciPy that constants can be pulled out of integrals, both for definite and indefinite integrals. Now, in earlier chapters, I explained why that is the case for single variable functions. And now here in exercise 2, we're going to demonstrate this same property for multivariable functions. In particular, the general point of exercise 1 is to demonstrate this equality. So for alpha is some scalar, some number that doesn't change as a function of x or y. The double integral of alpha times the function equals the single integral of alpha times the integral of the other variable. So in this case, we are pulling alpha out of the integral for x, but not out of the integral for y. And here we're pulling the alpha, the constant factor, out of both integrals. Okay, so I hope that makes sense. I also hope that this statement here, these equalities, are intuitive based on what you have learned earlier in the book regarding single variable functions. Okay, now there are 6 parts to this exercise, so it's rather involved. I am going to swap back and forth between the book and the code to go through each of these 6 parts in turn. Okay, so the first part, actually, I think I'll do the first 2 parts here together. So the first part is to implement this equation here as a symbolic expression. And then you see we have this factor e to the pi. And then you want to factor out that constant. There's no x or y in this term, so it is not it's not a variable term, it's a constant term. So pull that constant out to have an expression of the form e times pi, or e to the power of pi, times f of x times y. Okay, and then print out these first 2 parts in SymPy and LaTeX, and it should look something like this. So here we have the original function. This first line is literally just rewriting this function up here, but implemented in SymPy. And then over here, you can see I've pulled out this factor of e to the pi. So this is the constant that we are pulling out of the function. This first part of the exercise is not so difficult, certainly not conceptually difficult in terms of calculus, but the code is, it's a good reminder of some features of working with SymPy. Okay, so here I define 2 symbolic variables. Here is where I create the expression, the symbolic expression for the function fy, and here I have the constant factored out. So here I'm defining some constant c to be equal to e to the pi, and this is symbolic natural exponential and symbolic pi, not numpy like this, which is just a number. We want to be working with symbols here. And then here I just divide out by c. Okay, now the reason why there's the simplified term here, let me get rid of that for a moment just to show you what this looks like. Okay, so here is the original function, and here is the original function in the numerator, and then e to the pi in the denominator times e to the pi. Okay, so just to make this look a little bit nicer, I have simplified this so that we get e to the pi out from this expression. Now this is interesting because I said factor out this e to the pi, but this term here actually does not contain an e to the pi. So in order to get an expression of the form alpha, here I'm using c, but in the chapter I used the Greek letter alpha. In order to get an expression of the form alpha times f, we actually need to introduce e to the pi to the power of -1. So e to the minus pi, which is 1 over e to the pi, to actually get that term in here. This is something that often happens in math when you're trying to simplify expressions. Part 3 of this exercise is to calculate these 3 integrals over here. Now, for this part of the exercise, we're only working with indefinite integrals. You can see there's no bounds of integration. We will get to that later. For now, you just want to print out and calculate in SymPy these 3 expressions here and see what they end up being. And then you can print them out again in LaTeX. And so here you see, so in this first row here, we have e to the pi embedded in the function. Here in the second row, we have e to the pi pulled out from the first integral, but still inside the integrand for the integral over y, the outer integral. And then finally, I've pulled it out of both integrals. Now this is the problem statements over here on the left, and over here on the right, we have the results. And so the resulting indefinite integrals. I will interpret these results in a moment when I show you the code. Here I define three variables, int for integer, 1, 2, and 3, and you can see this is, here I'm using fxy, so the variable corresponding to the original equation. Here I'm using fxy fact. This was with the constant factored out. And then here I'm multiplying by c outside of the first integral, so here integrating over x, but inside the second integral over y. And then, of course, here we have the constant term completely pulled out of both integrals. And then, yeah, I'm just using sim.latex in combination with display and math functions to display the integral. Remember that when you use sim.integral with a capital I, all that's doing is going to print out the integral, print out the function as an integral. And then the actual integral itself, this is the answer here. That's what's printing out on the right. Okay, so what do we see? The main take-home message here is that the right-hand sides of these three expressions with the constants in various places are all exactly equal to each other. Now, on first visual inspection, it's obvious that the second and the third results are equal to each other. It initially looks like this first result is not the same as these other two, but it will take only a moment's inspection to see that this result here, this integral up here, has e to the pi, no e to the pi here, so we need to divide by that, and then an e to the pi here, and an e to the pi here. So if you factor out an e to the pi from this integral, this result, then you will get exactly the same thing as these other two results here. Now for step 4, where we move from the indefinite integrals to the definite integrals. Now, on the one hand, if the indefinite integrals are the same for the three expressions, of course, the definite integrals will be the same as well. How could that be any different? But adding this is just a great excuse for me to help you improve your Python and SymPy and calculus coding skills. Okay, so what you want to do is implement these three definite integrals in SymPy. So we're going to get exact analytic solutions to these definite integrals here. And again, no surprise at this point, we have the constant inside both integrals, inside one integral for y, but outside the integral for x, and outside both integrals. So here you can see I didn't actually print out the exact result. I printed out the numerical evaluation to however many numbers this is after the decimal point, like 10 or something. So yeah, and again, the key point is that these three numbers are all the same, showing yet again that constants can be pulled out of however many integrals we have. The three lines of code here are really, really similar to the corresponding three lines of code above for part 3. The only difference is that instead of just listing the variable that we are integrating over, we provide a tuple that indicates the variable to integrate over and the lower and upper bounds of integration. And now in this case, for this first line here, we are integrating over two variables. So I'm providing three inputs. The first input is the function object as the SymPy object. And then we have the inner integrand information and the outer integrand information. And then, yeah, these other two lines of code here, I'm only integrating over x. So in fact, the output of this sim.integrate call will be another function, but it's only a function of y, not a function of x anymore. And then I'm multiplying that by the constant and then integrating again over y. Okay, and then here is the same thing, except the multiplication by the constant happens outside of all the integrations. Okay, then printing the results. Yeah, and here in this case, I'm using .eval f to evaluate these functions to get individual number or specific floating point numbers. If you want to see the exact result, that looks like this. Yeah, I don't know what to make of that. There's a lot of symbols going on in there. The fifth part of this exercise is to repeat the definite integral calculation that we just did, but now using SciPy's integrate library instead of using the SymPy library. Okay, and now just to make things a little bit more simple, I've only pulled out the constant of integration once. This also makes it a little bit easier for the coding. So the double integral of the original function in SciPy's integrate. In fact, you can use the function double quad, so DBL quad function in the SciPy integrate library. Now, I have not yet in this chapter introduced how to use this function, double quad, but the usage is really, really similar to how you use the quad function in the SciPy integrate library. And I already discussed that several times for single variable integration. This reference is not compiling because I'm only compiling this particular chapter, but earlier in the book, I introduced how to use the spi.quad function for single variable integration, and now you have to figure out how to adapt it to double quad, so to double integration. Okay, it's not that hard, and I will show you the result in a moment. But yeah, basically we want to reproduce the result from SymPy, but using numerical approximations instead of exact calculations. So here is what this function call looks like. Now, you'll remember from when I introduced using spi.quad that the way that this function works is by implementing or inputting a function, which can be a lambdafied function from a SymPy expression like this. So I'm lambdafying the original function. And then for single variable function, you would provide two additional inputs corresponding to the two bounds of integration. So now we have the same concept here, except this function here corresponds to a two-variable function. And then here we provide 4 additional inputs instead of 2. And of course, we need 4 inputs because we have 4 bounds of integration, 2 for y and 2 for x. So this is a good opportunity for you to learn how to use the double quad function. And then here, this second line is very, very similar, except I'm using the factored function. So where I've pulled out the constant, and then I'm multiplying that constant here. And you also just have to be mindful with variable types here, because spi.doublequad and spi.quad is not going to accept symbolic variables. Instead, you provide floating point numbers, and that's why I have to convert all of the symbolic values into floating point values. Okay, so with that implemented, then we can reproduce exactly the same results that we got in SymPy. And finally, the sixth part of this exercise is to write matplotlib code to visualize this two-dimensional function. That's what you see as this image here, and a rectangle on top that indicates the area that we are integrating over. It's a pretty neat looking function. This last part of the exercise is not so difficult. If you are struggling a bit with the syntax for the matplotlib code, then I recommend just checking earlier in the chapter for the code where we produced similar figures. Okay, so here I have the x values, and you can see that the x values go from the bounds on x from a little bit below the bound to a little bit above the bound, and same for y. That's how we're going to get the image to be larger than just the bounding box of the window of integration. And why did I choose to go left 2 and plus 3 for x and y? These are arbitrary choices. You can try playing around with these. I picked these numbers after trying it a few times and just, these are just produced a range of values that I thought looked nice in the plot. Okay, so then create a mesh grid based on these x and y linear values and then lambdafy the function. And this is how we are going to create the image. You can see I'm inputting x and y, and that is the image that we show here. And then adding that rectangle I do with the rectangle function in the patches module of matplotlib. So that was imported earlier. Okay, then we just add that as a patch. Again, all of this code here, I have just copied here from one of the figures earlier in the book text. And then we get our final result. Welcome to exercise 2 of chapter 19. The goal of this exercise is basically just to reproduce this figure. So what are we looking at here in this figure? This is so the background image is a two-dimensional function. It is this here, e to the minus x squared minus y squared. This is a two-dimensional Gaussian. It creates this blur, this white blur, and it's often used, for example, to smooth images, to smooth pictures in image processing. That's one of the applications of a two-dimensional Gaussian of this form. And then we see these functions, these two functions drawn on top, and an area drawn between them. These two functions are y cubed is this one here between the bounds of 0 and pi over 4. And here we have the cosine of 2 pi times y using the same bounds between 0 and pi over 4. Now, these are the variable bounds of integration, and your goal is to calculate the definite area of this two-variable function using these bounds. Now, what I want you to do for this exercise to reproduce this number here is calculate the total area, not the net area, the total area. You can see that the total and net areas will differ from each other because these bounds actually cross each other. So this is the lower bound in the beginning and the upper bound. But here we have the upper bound dipping below the lower bound. So if you also calculate the net area, you can see what that result ends up being. But for now, for this exercise, I want you to calculate the total area. Now, before switching to code, I want to show you figure 10 from earlier in the text from this chapter, just as a reminder of how to calculate double integrals with variable windows of integration. So the idea, which you will see implemented in the code, is that you have to first integrate along each slice of this cutout area, and then you integrate across x. And then once you've gotten all of the little integrals, the slice integrals, up to however many slices you have, then you integrate again over y for all of those integrals. Here you see I'm creating symbolic variables, the symbolic function, and its lambda expression. And here we have the bounds of integration for x and for y. Now, if you like, you can try integrating this function, calculating this double integral analytically in SymPy. And basically what you are going to find is it's going to take a really, really, really long time, and it will not resolve. Eventually, the Python session will just crash. It's not going to work. So try to run this and go for coffee, have a nap, do some other work, hang out with your friends, and then come back and check on the result. Okay, and now here for the double integral. Okay, so here is the for loop that implements this double integration as I just explained from showing figure 10. So first we define the different slices of y. So that is here. So for the lower bound of y to the upper bound of y in 1,000 steps, this means that we are going to have 1,000 slices for the outer integral in which we will calculate the integral of each of those slices for each value of y in the range of the function. Okay, that looks like this. So I have a for loop over all of the values of y, and then within those values of y, I need to calculate the lower and upper bounds, and then some function values here. So 100 values between the lower and upper bound for x for this particular value of y as we are slicing up the function. Then we get the values of the function for these x values only. So these are the x values within this one slice, and this is the y-axis coordinate of that slice. And then here I call this a mini integral. This is not a formal mathematical term. This is the integral of this little slice, right? So we have isolated the function, the two variable function, for one particular value of y, and then we are integrating for all the values of x that are bounded by the variable windows of integration for this particular value of y. Now, once we have finished with this for loop, that means we have cut all of these slices and integrated over all of these slices. And then we have to take all of these integrals over x and integrate them again over all the values of y. Okay, I hope that makes sense. It's all quite a lot to keep in your head, but I described this in quite a bit of detail earlier in the chapter. And that is how we get this integration of 0.3896 and so on. Now, this is the total area of that function. Remember when I showed the image, actually, okay, I'm going to talk about the net area, but I'll get back to that in a moment. Okay, here's for the visualization. The visualization is a lot easier to do. Let me see. So here I am getting the z values from the function, the two-dimensional function. Here I am extracting the numerical values for the variable window of integration. So this is the x-axis variables. These are the y-axis variables over here in two separate arrays because we have two separate functions that we need to deal with. So for the lower bound and the upper bound of integration. Okay, so let me show this plot. There's a lot of lines of code here, but I think it's not so, there's not a lot of new code here for you. Okay, so now in theory, the integral, we might intuitively expect the integral to be positive no matter what, because this background function that we are integrating over, e to the minus x squared minus y squared, this function is strictly positive. It can never be zero, and it can never be negative, because e to the anything is going to be a positive number, even if that number is itself a negative number. That said, the bounds of integration here actually swap. So here we have the lower bound and the upper bound, but then the lower bound goes over the upper bound. Okay, so this means that this shaded area here is going to contribute negatively to the area, and this shaded region will contribute positively to the area. So this is the number for the total area, 0.389. That's the total area. And it's the total area because we have the absolute value function over here. So we are taking the absolute value of these slice integrals. Now, if I remove this, then we are going to calculate the net area. And what do you think? What's your intuition? Is the net area going to be positive or negative? My intuition from visual inspection is that the net area will be negative because all of this area here looks bigger than this area here. Now, the thing you have to be mindful of is that we are not integrating this area and this area. We are integrating the values of this two variable function in this area and this area. Okay, so it's, brighter white colors here indicate larger values of the function. So this might be more area, but if the function values are smaller, then it's going to contribute less. Okay, I hope that makes sense. Let me give another example. Imagine, you had some area that was maybe even larger than this, but it was all the way out here where the values of the two variable function are really small. So maybe the area is bigger, that counts negative, but the values of the function in that area are really, really small. So their negative contribution to the net area might be very, very small. So it is not trivial that just because this area is smaller and this area is larger, that therefore the net area will be negative. Okay, I hope that makes sense. It depends not only on the size of the area, but on the values of the function underneath those two areas. All right, that said, it turns out that if you calculate the net area, it does end up being a little bit negative. It's around minus 1.3 is the net area. This is the video for exercise 3 of chapter 19, but I want to start this video by showing again figure 10. Now you've already seen this in the book, and I showed it also in the previous exercise, but this figure nicely illustrates the goal of exercise 3, and I will explain the exercise in a moment, but first let's just have a look back at this figure. So we have some function in the background, x squared plus y, and we want to calculate the area of that function within some window of integration that is variable. So it's not just a box on the x and y axes. Instead, it is drawn by a curve that is defined by some functions. In this case, it's y and y squared over here. Okay, so remember, the idea of calculating this double integral, at least empirically, when we want to estimate it empirically, is to slice this region into a bunch of thin slices going up the y-axis. And for each slice, then we integrate over this function so in this case, it will be x squared for this particular x-axis value. I'm illustrating here 0.4. So we have y equals 0.4. And then we integrate over x squared from whatever these bounds end up being for when y equals, 0.4 and then 0.4 squared. Now, when we integrate over here, we need to define a delta x. So we need to define a resolution for the x-axis for cutting up this slice into individual pieces, which we then sum using Riemann sum. So how do we, so if we define delta x to be some constant value, maybe 0.01, for example, then that means that the number of points in this slice is going to vary as a function of y. And why is that the case? Because when we have this thin slice down here, there's very little space on the x-axis. So there's only going to be a couple of points here. And similarly up here, when we get to this slice here, this slice is very thin. So there's only a couple of points here. And this slice is thicker. So there's more x-axis values here and fewer x-axis values over here and fewer x-axis values over here. So that means that the number of points that we are integrating over depends on the thickness of the slice. That's intuitive, but that means that it depends on the value of y as we are going through this variable window of integration. Conversely, if we were to say, well, we always want to have 100 points of x to integrate over, well, 100 points here for slice 1 is very, very small, so delta x will be tiny, versus 100 points spanning this x-axis subdomain here is going to involve a larger delta x. And then here we have a smaller delta x. And with that illustration, that concept in mind, now we can get to the instructions for exercise 3. So the goal of exercise 3 is to explore exactly this concept that I just described, but more quantitatively. Okay, so the first goal of this exercise is to modify, copy, paste, and modify the code for figure 9. I was showing you figure 10, but figure 9 is the same thing, just without the labels on top. And what I want you to do is calculate the value of delta x that you get for each value of y, assuming a fixed number of 100 x-axis points between the two bounds for each value of y. And that result is going to look like this. So for small values of y, delta x ends up being really, really tiny because we have 100 values of x that we are splitting up from a tiny little area. So delta x ends up being small. And then when y is towards middle values, then we end up having a large value of delta x, and so on. It gets smaller again. Okay, so that's the first part of this exercise. The second part of this exercise is to repeat this experiment, but now instead of holding the number of x-axis values constant and seeing what delta x ends up being, now instead you fix delta x to be 0.001 and you count the number of x-axis points for each y-axis value or for each of these slices. Okay, and not surprisingly, it's also going to be a inverted U-shaped function. Okay, there's a third part to this exercise, and I'm going to get back to it in a moment. But first, I want to show you the code and discuss these intermediary results. The code in this cell generates this function as a symbolic expression and then lambdafies it so we can use it later to get specific numerical evaluations. Here I define the two bounds, and here is where I get the definite integral through SymPy. Now, SymPy can actually integrate this definite integral. This code here, this whole code cell is literally copy-pasted from the code that generates figure 9. It's just reproduced here. Okay, so let's run that. And now the code in this cell looks like the code for the double integration with variable bounds that you have seen in the previous exercise, and also in the code for exercise figure 9. But this code is a little bit different because for this part of the exercise, for parts 1 and parts 2, actually, we do not actually need to integrate any functions. So there's no integration code here. Instead, what we want to do is fix the number of x-axis points to determine the delta x, and fix delta x and determine the number of points. So this is going to produce that figure in the book that I just showed with the two upside down U-shaped functions. So here I am looping over all of the y-axis values, and then I'm getting the lower bound and the upper bound, and this is basically finding the bounds of integration for this particular slice, this particular value of y. Okay, and now here what I'm doing is getting 100 linearly spaced points between the lower bound for x and the upper bound for x for this particular slice of y. And then I'm empirically calculating the delta x for this slice on the y-axis for assuming 100 values of x. So this is the first part of the exercise that's going to create the left side panel, so panel A of the figure. And now here, this code is similar, except now here I'm fixing delta x to a value of, what did I say, 0.001. So delta x is 0.01, and then I just want to know how many x-axis values are between the lower bound and the upper bound for this fixed value of delta x. So this is the number of x-axis values. Okay, so this is parts 1 and parts 2 of this exercise. And we see that, as I showed in the book, in both cases, delta x and the number of x-axis values ranges. They vary as a function of the x-axis value. Now, it is not trivial that the delta x and the number of x-axis points follows this inverted U-shape. It follows the inverted U-shape because of these specific bounds of integration that I used here. So y and y squared. That's why they pinch here, so they're close together. The bounds are close together. Here the bounds are further apart, and here the bounds are closer together again. So the point is that the delta x and the number of x-axis points can vary as a function of the variable bounds of integration. Now you might be wondering, does this have any implications for the accuracy of the numerical approximation? That's a great question, and that leads us to the third goal of this exercise, which is to evaluate the accuracy of the empirical approximation of the integral by comparing the numerical approximation of the integral against the definite integral that we got from SymPy with a known exact value. Okay, and we're going to do this over a for loop, in a for loop ranging over different delta x values between 0.0001 and 0.01. Okay, and then the result you will get will look something like this. So in the first part, let me just make sure that this is super clear. So here, what we did in this second part of the exercise is fix delta x to be 0.001, and then we found that the number of points varied for this fixed value of delta x. And now what we are going to do is actually integrate the function. Right here, we did not integrate the function, we just counted the number of points. But now we really are going to perform the double integration to get a numerical approximation of the multivariable definite integral using this variable bounds of integration for a range of delta x values from whatever it was, 0.0001 to 0.01. And that is plotted on the x-axis here. You can see I've swapped the order. So it's actually starting at larger values of delta x and going up to smaller values of delta x. And here on the y-axis, we have the approximation error. So this is the difference between the numerical approximation of this double integral using each of these delta x parameters and the exact definite integral that we got from SciPy. And that code you see over here. So here I'm setting up a range of delta x's from 0.0001 to 0.01. I'm using 19 steps. You can also use 20 or 18 or 100 as you like. And here's where we are running this exploration. So in this case, we have a for loop over all the different values of delta x. And then here is where we implement the numerical approximation of the double integral. So here, this for loop here is ranging over all the values of y. So it's getting all these slices of y and then calculating the integral over x for each value of y. And then here is where we integrate a second time over all of the values across x. So this is the outer integrand over here. Now we don't actually need to store the integrand itself. We only need to know the error, the discrepancy relative to the true value, the analytic result from SciPy. So that's why I'm only calculating the outer integral here, because we don't need to know the actual numerical value of the integral. We just need to compare it to the symbolic, the exact calculation. Okay, run that code, and then, yeah, the rest of this is just plotting, so that's fine. And here this is where I invert the x-axis here to get the smaller values on the right and the larger values on the left. Okay, now what does this mean? What do we learn from this? Now, keep in mind that this is not an issue that plagues abstract mathematics. In abstract mathematics, there is no delta x. We have a dx. So it's always an infinitesimal, really, really tiny, vanishingly small value of delta x. But on computers, at least for analytic or numerical calculations, we cannot actually just have dx. We need to define some delta x. And so basically what this shows is yet another illustration that the smaller the delta x, the more accurate your calculations are going to be. Now, on the one hand, that is not so surprising, but on the other hand, this is a real issue that you will encounter every time you do integration type problems with real data sets. So numerical data that come from measurements of the world and not necessarily from mathematical functions that can easily be manipulated and integrated symbolically.